Welcome to our lecture on group theory. Today, we are going to explore a beautiful and powerful concept known as group isomorphisms. If you have ever wondered how mathematicians connect seemingly unrelated systems to reveal hidden similarities, you are in the right place. Let us dive in and uncover the secret structures of mathematics. To understand what an isomorphism is, imagine you are playing a game of chess. You normally use standard wooden pieces like knights and rooks. Now, imagine you lose your set, so you decide to play using coins, bottle caps, and buttons instead. The physical objects you are holding are completely different. However, the rules of how they move, interact, and capture each other remain exactly the same. In mathematics, when two systems look completely different on the surface but share the exact same underlying structure and rules, we call them isomorphic. The word comes from Greek, where iso means same and morph means shape. Now that we have an intuitive understanding, let us look at the formal requirements. To prove two groups are isomorphic, we first need a special mathematical tool called a bijection. Think of a bijection as a perfect one-to-one matching between two sets of items. Every single item in the first set must connect to exactly one unique item in the second set, and absolutely nothing can be left out. It is like assigning exactly one unique seat to every student in a classroom, with no empty seats and no students left standing. This two-way street ensures our translation dictionary is complete. While a perfect matching is necessary, this brings us to the second critical requirement. A bijection alone is not enough to create an isomorphism. The matching must also possess a property called operation preservation. This means that if you combine two items in the first group and then translate the result, you must get the exact same answer as if you translated the items first and then combined them in the second group. Only when a mapping has both a perfect matching and operation preservation is it officially considered an isomorphism. Let us translate this idea of operation preservation into a mathematical formula. The equation you see here is the fundamental test for any isomorphism. The symbol phi represents our translation function, or the dictionary mapping elements from the first group to the second. The star symbol represents the mathematical operation of the first group, like addition. The diamond symbol represents the operation of the second group, like multiplication. This equation literally says that combining A and B first and then translating the result is perfectly equal to translating A and B individually first and then combining their translations. If this holds true for every pair of elements, the structure is preserved. Before we move on to a concrete example, let us visualize this operation preservation. On the screen, you see two distinct groups, labeled Group G and Group G bar. Notice how the elements A and B in the first group map directly to phi of A and phi of B in the second group. When we combine A and B using the star operation, we get a new element. If we map that combined element over, it lands on the exact same spot as if we had combined the translated elements using the diamond operation. The blue arrow represents this perfect structural harmony. Now that we have our formula and visual intuition, let us see this with a concrete example. We will look at a classic case involving real numbers. Our first group consists of all real numbers under the operation of standard addition. Our second group consists of only strictly positive real numbers under the operation of standard multiplication. We want to prove that these two completely different looking groups are actually isomorphic. To do this, we must invent a translation dictionary that connects every real number to a positive real number. We choose the exponential function, e to the power of x, because it naturally turns addition into multiplication. With our translation function defined, we can begin proving the isomorphism. First, we must verify the bijection. The expression e to the power of x takes the mathematical constant e and raises it to the power of x. Because this exponential function is always positive and strictly increasing, it perfectly matches every real number to a unique positive real number, satisfying our one-to-one requirement. Next, we test the operation preservation. We take two real numbers, x and y, and combine them using the first group's operation, which is addition. We then plug this combined sum into our translation function. Continuing from our previous step, we now apply a fundamental rule of algebra regarding exponents. When you have a base raised to a sum of two numbers, it is mathematically identical to multiplying the base raised to the first number by the base raised to the second number. This step is the magic bridge in our proof, physically turning our addition problem into a multiplication problem. Finally, we recognize that e to the power of x is simply the translation of x, and e to the power of y is the translation of y. Substituting our function notation back in, we see that translating the sum equals multiplying the translations. The operation is perfectly preserved. So we have proven that infinite groups can be isomorphic. This brings us to a finite example using modular arithmetic, which is like math on the face of a clock. Our first group is the set of integers modulo 4 under addition, containing the numbers 0, 1, 2, and 3. Our second group is the group of units modulo 5 under multiplication, containing the numbers 1, 2, 3, and 4. Since both groups have exactly 4 elements, we need to match them up one-to-one. The best strategy here is to find a generator for each group, which is a single element that can create the whole group by repeatedly combining with itself. Continuing with our modular arithmetic groups, let us find the generator for the first group. The number 1 acts as a perfect generator here. If we repeatedly add 1 to itself, we generate all the elements of the group: 1, 2, 3, and finally 0 when we reach 4. This happens because we are using clock arithmetic, modulo 4, meaning the numbers wrap around after reaching 3. Now we move to our second group, where we use multiplication modulo 5 instead of addition. We need to test the number 2 to see if it can act as a generator by repeatedly multiplying it by itself. Let us finish building our translation dictionary. In our second group, multiplying 2 by itself gives 2, then 4, then 8, which wraps around to become 3 modulo 5, and finally 16, which wraps around to become 1 modulo 5. Because the number 2 successfully generates all 4 elements, it is the true generator for the second group. We define our final function to take any number from our first group and use it as the exponent for the number 2 in our second group. This perfectly maps the generators, proving beyond a doubt that the two groups are isomorphic. Now that we have seen how to prove isomorphisms, you might wonder why mathematicians and scientists care so much about them. The main reason is that it saves an enormous amount of time and effort. If you discover a brand new mathematical group in your research, but you can prove it is isomorphic to a group that has already been studied for hundreds of years, your work is instantly done. You can immediately apply all the known theorems and properties to your new group. This concept allows scientists to classify complex systems into simple categories, which is incredibly useful in fields like quantum mechanics and cryptography. To wrap up our lecture, let us review the key takeaways. A group isomorphism is a perfect structural translation between two mathematical systems. It requires a strict one-to-one and onto matching, known as a bijection, that perfectly preserves the rules of combination. When two groups are isomorphic, they are fundamentally the exact same object, merely disguised by different symbols and operations. Understanding this powerful concept allows us to simplify complex problems by translating them into familiar, well-understood territories. Thank you for joining this exploration of group theory.